Hello, my name is John Cody. I'm an engineer from Vancouver, Canada, and today we're continuing on with our exploration of the quadria of the projective quadrangle. The setting is projective geometry, in particular universal hyperbolic geometry and projective elliptic or spherical geometry. Last time we showed that the quadria of the projective quadrangle is given by these two quadratic equations that are compatible, and we proved that these two quadratic equations are compatible by the quadratic compatibility theorem. And they have a common solution given by this expression. So these are two quadratic equations in A, and they have a common solution given by this. And we proved it in previous videos in universal hyperbolic geometry, but in this video we're going to show it. We're continuing with showing it in elliptic or spherical geometry. So we have four projective points forming a quadrangle A1, A2, A3, and A4 with quadrances Q1, Q2, Q3, and Q4, and spreads S1, S2, S3, S4. So here in the hyperbolic setting, we have the distinguished circle and the projective plane and these four projective points, A1, A2, A3, A4. And they use this quadratic form, x squared plus y squared minus z squared. In elliptic or spherical geometry, we use this quadratic form, x squared plus y squared plus z squared. There's a plus here. And so the projective points are lines through the origin, and they appear on the surface of the sphere as A1, A2, A3, and A4. And we're interested in the quadria of these four projective points, or the quadria of the quadrangle formed by these four projective points. Okay, so what we're going to do in this video is substitute our expression. Oh, and I'd like to remind you that the quadria of the projective quadrangle is given by these two quadratic equations that are compatible, and the same equations can be used in universal hyperbolic geometry as well as elliptic or spherical geometry. They are exactly the same. They use exactly the same equations, and we'll show that in this video. If we in elliptic geometry, that these equations are valid when we're going to substitute this equation for A back into one of these two equations and show that the left-hand side is equal to the right-hand side. Okay, so we went through the definition of the quadratic compatibility theorem in the previous video, and we saw that we had this expression for x. The common solution is given by this expression in Mathematica, which is just this formula right here. And when we substitute the values for P1, R1, P2, and R2 of these two compatible equations, and in these equations, P1 is this quantity here, R1 is the right-hand side of equation 1, P2 is the quantity here, and R2 is the right-hand side of equation 2. So we substitute those values into the formula for x to get A, and this is A right here. This is just restating the quadria of the projective quadrangle theorem. I won't restate it, but here it is. So in part 1, we proved that these two quadratic equations are compatible. So next we compute the quadria A using the formula for the unique common solution of the quadratic compatibility theorem and substitute it into equation 2. So we're going to substitute the formula for A into this equation and verify that two sides of the equation are equal. So we're going to substitute the quadratic equation. We're going to substitute A in quadratic equation 2 and expand the left-hand side and the right-hand side of equation 2. We will So we're using Mathematica functions expand, factor, together, numerator, and denominator to perform algebraic manipulations. So the left-hand side is this equation here. So it's going to be A minus Q1, Q4, S1 minus Q2, Q3, S3. All of that squared. So this is it here. And we're going to expand that out, and we get the variable left-hand side E, left-hand side expanded. We're calling the Mathematica function expand on this left-hand side, and that gives us this expression here, this long expression when we expand it all out. Next, we're going to call the together function of Mathematica on this expression up here. So it's left-hand side expanded together, and that will put it over a common denominator. So this is what we get when we call the function together on left-hand side expand, and we get this common denominator down here, divided by this. Here's the common denominator. So the numerator of the expression up here is, we're going to call it left-hand side enum. So left-hand side expanded numerator is we're calling numerator, which is a Mathematica function on the left-hand side ET variable. And similarly, we're going to get left-hand side denominator on the same equation, which gives us this expression. Here's the denominator right here. The right-hand side is given by this expression, and the denominator of the right-hand side is just 1. Next, we're going to multiply the right-hand side by the left-hand side denominator, which we're going to multiply this by this to give us this expression here. And then we're going to expand this expression all out to get this. So this is the right-hand side multiplied by the left-hand side denominator all expanded out, is this quantity, this expression here. So what we'll do next is we'll subtract the left-hand side numerator minus the right-hand side multiplied by the left-hand side denominator expanded to give us the result, which is this long expression here. So this gives us the result we're looking for in terms of the quadrances and spreads. So next, what we'll do is we're going to substitute into these quadrants the definition of these quadrances and spreads in terms of the projective points. So projective point A1, which is the point given by x1, y1 to z1. Projective point 2 is x2 to y2 to z2. A3 is x3 to y3 to z3, and A4 is projective point x4 to y4 to z4. And then we're going to call the join. We're going to define the join of 2 points using the quadratic form of elliptic geometry, and that's given by this expression. Similarly, we're going to compute the quadrants between projective points. It's given by this function, and again, it's using the quadratic form of elliptic geometry, so it has a plus here, and a plus here. And similarly, for the spread between 2 lines is given by this function, is given by this expression. Again, it uses the quadratic form of elliptic geometry. So next we're going to compute the quadrants between projective points A1 and A2. That's Q1. So we're calling this function that we defined up here to give us Q1. Q2 is the quadrants between A2 and A3. Q3 is the quadrants between A3 and A4. And Q4 is the quadrants between A4 and A1. And that results in these four. This is Q1. This expression here is Q2. This expression is Q3. And this expression is Q4. Notice that it has a plus sign here, here, and here in front of the z's. Next, we're going to compute the lines L1, L2, L3, A4, which is the joint. L1 is the joint of projective point A1 and A2. L2 is the joint of A2 and A3. L3 is the joint of A3 and A4, and L4 is the joint of A4 and A1, and that's given by these quantities here. These are projective lines, so they're proportions. Next, we're going to compute the spreads. S1 is the spread between line L4 and L1. S2 is the spread between L1 and L2. S3 is the spread between L2 and L3, and S4 is the spread between line L3 and L4. And so this is S1. This is S2. S2 is given here. This is S3, and this is S4 in terms of X, Y, and Z. And next, we're just going to call factor on our result, RES, to give us a result. So that back up here, RES was the long expression. It was the left-hand side minus the right-hand side. So we're going to substitute the values we computed for all the quadrances and spreads in terms of the X, Y, Z in this long expression here, and then factor that all out. And we're hoping to see a left-hand side minus the right-hand side is equal to 0. So when we factor it all out, we should see 0, which is what we do see. So we get the result of 0. Okay, so what we did was going back to the top here, here's the quadrea of the projective quadrangle as given by these two formulas. And we substituted, and these are two quadratic equations that are compatible, and they have a common solution given here, common solution A. And what we did was we substituted this expression for A into equation 2 and expanded it all out and subtracted the left-hand side from the right-hand side and got a value of 0. So we just verified that that all worked out. Okay, thank you.